Okay, Shloka, what are we doing today?
Today we're going to learn about a pendulum.
Okay, what is a pendulum?
A pendulum is a clock that they used to use in the olden days.
Before electronic digital clocks were invented.
Yeah.
Where do you find them?
You can find them in museums or mansions.
Okay.
Yes.
So what are the key terms here?
An oscillation is the time it takes to go and come back to where it first was.
We call that time period.
Mm-hmm.
Okay. So
An oscillation is that, but the time it takes is a time period.
Okay. So who discovered these laws of pendulum?
It was somebody named Galileo Galilei.
When did he live?
He lived in the 17th century.
Okay. So he did lots of things besides astronomy, right? So this is one of the things. So today we're going to rediscover the laws of pendulum with ourselves by doing some experiments, right?
Mm-hmm.
So what are the experiments we're going to do today?
We're going to find out
what affects the time period.
Is it the angle? Is it
So the angle meaning this one, right? So
big and the small angle? So the big angle is like this and the small angle is like that. So we're going to see, will that affect the time? Or will the length of this affect the time? Or will
the weight of the pendulum.
weight will affect?
So is it possible to measure the time it takes for exactly one oscillation?
No. So it is possible, but it will be very hard. So let's just do 20 instead of 1.
So we'll do 20 oscillations, find the total time, and then I guess divide by 20.
Yeah.
All right. So I will use the stops clock here to keep track of the time and record it. Okay. So let's start with small oscillation. Okay. Go ahead.
Okay.
Wait. Yeah.
1, 2, 18, 19, and 20.
It is 41.15 seconds for 20 oscillations. Now,
Let's try the big
wide angle. Go.
1, 2, 3, 18, 19, and 20.
So we got, for wide angle, we got 41.4. So for small angle of oscillation, we got 41.15 seconds, and for a wide angle of oscillation, we got 41.4 seconds. So what's the conclusion?
It's pretty much the same, so that means that the angle doesn't affect the time.
Correct. So that small error we got is statistical noise or some error in the calculation of timekeeping.
If we had like more approximate,
More precise
instruments, then we could get the same exact answer.
Yeah, we can eliminate that minor error. Okay, so that is the first experiment which shows that the time period is not affected by the angle of oscillations. But what if I add some weight? Do you think that can possibly affect?
I don't know, there's only one way to find out.
So let's add some weight here. Okay, so I'm going to add this weight here. So let's now repeat this experiment again for 20 oscillations and see if we get any different answer than approximately 41. All right. Yeah, go.
Okay. 1, 2, 18, 19, and 20.
Okay, so with weight, we got 41.3. So here are the results. Without weight, for 20 oscillations, it was about 41.15 seconds. And with weight, it was 41.3 seconds. So what's the conclusion?
So it's about the same again. So the conclusion is that the weight also doesn't change the time.
Okay, good. So what is the third experiment now?
Third experiment is the length.
Okay,
Ta-da! Now we decreased it by half because first it was 100 centimeters and now it's only 50. So let's see if the length will change the time period.
Okay, we're going to do 20 again, yeah? Wait. Yeah.
1, 2, 18, 19, 20.
So now with 50 centimeters for 20 oscillations, it was 29.7 seconds. So here are the results, Shloka. For 100 centimeters, it was 41.3 seconds. For 50, it was 29.7. So how do you interpret these results?
So you might have thought that cutting the length in half would make the time taken in half too, but that's not true. It's actually going to be multiplied by the approximate square root of 2.
Well, actually, in this case, well, that's right. But if you are doing 50 over 100, as you did, it is dividing by square root of 2. So this is the law discovered by Galileo in the 17th century, okay, for which he became very famous, actually. So the length of the pendulum does affect the time period, and the precise relationship is if you double the length, the time period doesn't get doubled, it gets multiplied by a factor of square root of 2. Okay? Now you might wonder, where is square root of 2 coming from? To understand that, let's take a closer look at the data here. So in this table, we have the first column, which is showing the length for 50 and 100, and in the third column, you have the time period, 29.7 and 41.3. When you compute the time periods, you get 1.49 seconds for 50 centimeters and 2.07 for 100 centimeters. When you compare the ratios, L2 to L1, that is 2. However, the corresponding ratios for T2 to T1 is approximately 1.39, which is a good rational approximation for square root of 2, which tells you that doubling the length of the pendulum increases the time period by a factor of square root of 2. The mathematical relationship is the time period is proportional to the square root of its length. Okay, finally here is the summary of the laws of the pendulum that we rediscovered using those 3 experiments. The first experiment told us that the time period does not depend on the amplitude, the angle of oscillation of the pendulum. The second one told us that the time period does not depend on the mass of the oscillating body. Even when we added the weight, we got the same time period. The last experiment told us that the time period does depend on the length, and the precise relationship is the time period of the pendulum is proportional to the square root of the length of the pendulum. So now, how is this affecting the times of the pendulum clocks in the different seasons?
In the different seasons, in the summer and spring, it would get bigger because heat expands, and in the winter and fall times, it would shrink because in the winter time things get smaller. So that made the time different. So that's why it wasn't very approximate. So that led to the discovery of digital clocks.
Later. Yeah. Good job, Shloka.
Okay. Bye, guys.